We're just gonna start. We're gonna be going over. We're gonna like kind of build like a little Chrome Dino Bot with some AI. It might be interesting, but first off, we have a USACO coming up. This is the third contest. It's from February 26th to March 1st. So basically, it's the same as usual. Though it's the third contest, which means like there's only one more after that, which is the US Open. And then so that means next week, February next week is February 3rd. Next week, February 3rd, we're probably going to be going over the past USACO contest and some tips and tricks from for USACO because someone requested that. All right, so now I'm going to stop sharing and I'll let Lucas share.
Okay, so I'm just gonna go over this like code briefly. So I have two different like um GitHub codes for the Dinobot. I think Eric will go over like how this works exactly later. But this is just like a brief description, I guess. So first of all, wait, I'm gonna reshare actually. Hold on. Okay, sorry. Um, so this is not my code, this is by someone else, but basically this one is much more, it's a lot longer, but it's a lot easier to understand basically. So all of this is pretty straightforward. All of this is in JavaScript. I don't even like understand the syntax of JavaScript that well, but you can kind of understand it just based on the um, some of the words and stuff. So it begins by declaring like a bunch of variables and stuff. And this just uses like a basic, I think pixel detecting system. So we know all the bushes are black pixels. So basically when it detects one, it's gonna jump. That's basically what it does here. So it's gonna use pixel data, and then it uses that pixel data to tell the dinosaur to jump. And then there's more than that. There's a couple of different things that happen in the dinosaur game. Um, First, there is the birds that show up, and you have to duck under them sometimes. So that's also included here. And then there's the color scheme change. So I think it's like every 700 points or something like that. It changes to like nighttime. So now you got to detect white pixels instead. But it's really just the same thing. So yeah, this right here is watching for birds in mid-level, because the mid-level birds, I think you can jump over them, but it's easier to duck under them. So okay, so that's all of this. I'll send this link in the chat right now, and then you could take a look of it more in depth. Okay, so I'm going to move on to the other one, the other code right here. So this one is a lot shorter, and this one actually works. So I'll show a little like demonstration in a little bit. So here you could tell that the code is a lot shorter. I think it just uses like a better algorithm, so that's why it's shorter. Um, I think I'll just show a little demonstration of this, and then um, okay, keep in mind this bot isn't like perfect. And there's a couple of different situations where it could die really early. So what you could do is go to Chrome //dino, and it gives you the press space to play. We're going to put in this code. So it's going to copy and paste. And then this is where all the gamers go to. You open inspect element, and the console is where you can put in this stuff. So this is pretty useful. Okay. Usually if you don't get an error, that means you're good. Usually sometimes even if it works, it's gonna give you like errors. So if it doesn't have like any errors, that means it's probably gonna work. Okay. So I'm not pressing anything right now. And it zooms in so you can tell. Okay. So this is the first case that pops up. Um, I can't really go back, but what happens is that there's two cacti like really close to each other, and what the dinosaur this code detects is that it only jumps at a like certain point before the because okay, for example, it's gonna detect this black pixel, and then it's gonna jump, let's say like 3-4 dots before the cactus. And if you do that, there's not enough time to jump before the next one if there's two that are really close together. So if a human was playing, we would remedy that by jumping earlier. So we land earlier and we can make another jump faster. But the bot can't do that. So that's that's why if two cacti show up really close to each other, the dinosaur is gonna die. But it did work for the first jump, so that means it's working. So let's play this again. Okay, I'm not pressing anything right now. See, you can tell it's kind of getting like awfully close to the cacti before it jumps. So that's why it might mess up sometimes. Let's just see how far this goes. But another thing is, if you're jumping close, there's no way. It's really hard for it to miss those long cactus jumps where there's like 4 of them or something. Like if a human was playing, it'd be really easy to miss those. But if a bot was playing, it's not gonna miss. Okay, so it learns to duck. And I think we're gonna get the color change pretty soon as well. And you see, it didn't really need to duck under that one, but it still did. That's just how the code works. Okay, so now it's detecting for white pixels basically, but everything is still kind of going according to plan. I think I'm gonna let this play just to see how long it goes. If it gets to like, wait, let's see if it could beat this high score. I think I got this high score actually when my internet went out. So let's see if it can beat the human. And you can tell that as it gets like, okay, it just beat my high score. As it gets faster, it's actually easier for the Dinobot because there's no longer going to be those cactuses or cacti like close to each other because um, the game designer thought like it would be like really hard to jump those because of how fast you are. So they reduce the number of like cacti that are clumped together as you get further. So that's why it actually didn't. The only part it can die is at the very beginning, where we can get that like cactuses next to each other situation. But now it's just gonna go on and on. Okay. So I'm gonna stop this, and then I'll give it to Eric to explain uh the machine learning stuff.
Okay, so I'm gonna share my screen. Um, Basically, first I'm gonna cover some quick terms because otherwise it might not make as much sense, and then we'll show the code and actually show like working. So first off, agent slash environment. Basically, the agent is like the theme. It's like the main character. You could think of it. It's what the artificial intelligence is. In our case, it's a dino, right? So whenever we refer to the agent, we're referring to the dino. And then actuators or like actions, those are the game options, right? Which are running, right? It's like not pressing any keys, right? Which would be running straight. Jumping, right? If you like hit spacebar or the up arrow, and then ducking, which is like the down arrow, right? Those are your three options in the game. There are no other options you can make. And then the environment is like where the agent is playing, where the agent is situated in. In our case, it's just the game, right? That little desert. And then we have some sensors. Sensors come from the environment, as you can see from like this visual. But basically, our sensors that we're going to be looking at is distance to cactus, height slash width of the cactus, the bird height, the speed of the game itself. So like how fast everything's moving, and then bias. We'll get to the bias part later. So that's all for agent slash environment, and then learning loop. So the learning loop, it's obviously it's a loop. The first step it does is it resets the environment. In our case, that would be restarting the game, right? Or like clicking play on the game, same thing. And then the agent picks an action out of the three I listed earlier, running, jumping, or dunking. And then it returns the reward, the game status, and the next state of the environment. Um, the reward we'll get to later. The game status is like if the game is still going, right? Like if the dino collided, right? If the game's over, it'd be like false, right? And then the next state of the environment would probably be just the next frame, right? The next like frame of the game, because we're going to be analyzing like frame by frame. And then your AI, the agent, it remembers the reward with the experience replay. The experience replay is it's just a thing. It's basically like the memory, and the AI can go back into this experience replay into this batch of experiences to learn based off those experiences. So we'll get to more about it later, but roughly you can just think about it like right. It has good rewards and it goes back and chooses some of those good rewards and it learns based off the good ones, right? Because you want to learn off your high scores basically. And then reinforcement learning, this is where everything ties together. So this is like the reward system, right? So your agent gets positive points, it gets plus points for doing something good. So for example, if it's achieving a high score, you know, you give it extra points, right? And an agent gets subtracted points, minus points, right? Negative points for doing something bad. So examples would be like dying or achieving a low score. And then obviously the agent wants to get the highest score as possible. And in our case of the Dino game, it's actually pretty simple because uh, there is a score counter for us, right? It has the score displayed constantly. So it's very easy for us to kind of like implement that too. The goal is that the agent can learn that, hey, jumping over a cactus equals plus points, which is good. So I'm going to keep on jumping over cactuses. And it just keeps on learning like that. And then so the AI learns from the word system and correlates certain actions to points. And we learn like this too. Um, when we were like babies or when we were like learning to walk, that's how we would learn. But we probably all forgot about that because like it was so long ago. But for example, like when you train a dog, like a trick or something, um, you give it like a treat after it does it correctly, right? Which is basically the same thing. You're making it correlate an action to a positive like memory, right? And then so last thing we have is the bias slash variance that we talked about on the first slide. And that's the randomness that affects the agent's decision. So it's kind of like a trade-off. Um, how it works is, let's say your bias is a variable, right? Is like extremely high. That would mean you have a very high bias. What would happen is that your agent would be have a high amount of randomness. So it would choose very random actions like on purpose to like test out the waters, right? So it's like when you're learning to walk, right? It would just test out a bunch of different methods instead of just doing what it knows. If you have a very small number for your bias, a very small number for the randomness, instead it won't be like venturing too far and doing so many different actions. It might just instead it knows that, hey, this gives me points, this is good, I'm gonna just keep doing this because I know for sure this gives me points. So it's not as risky, um quote unquote. And so you want to have like a stable number for your bias because too high and it might take forever to learn because it's doing all this weird stuff. Too low, it might never learn properly because it never ventures far enough to try the correct solution. So that's why you have to like kind of tweak your bias size variance here and there. And in genetic algorithm, um, this ties in back to like science and like biology and like Darwin's theory of natural selection, if you guys remember that. So basically, it's the same thing, except there's a population of dinosaurs this time. So you have like a certain amount of dinos, is like in the hundreds, right? Well, as many as you can, but your computer might not support it, right? But whatever. And then you have a lot of dinos, and then when they die, they die. But the ones that do well and survive and get like a high score, they reproduce and create more dinos. And those dinos, those new generations, they retain the same features as their parent, but with some variance. And the variance is the thing that we just talked about, right? So with some like uh, difference here and there, some randomness. And so basically it's very similar to natural selection, except we also have like a fitness value, which is how good the solution is. So for example, fitness value basically determines if the dino is like chosen for reproduction. So it says that dinos with high fitness values, right, so high quality solutions, they have a higher probability of like being selected from like the mutation pool for reproduction. And so how to calculate the fitness value? Normally, we just calculate using our score, right? The reward. The higher the dino score is, the better it is. And we want to choose the dinos with the highest scores. Um, and then, so let's say a dino gets a score of like 100 and another dino gets a score of 99. Obviously, we would want the dino which has a score of 100, right? Because it's higher than 99. However, it's not that much higher than 99. It's barely any higher, especially when you consider how far the game goes and like the true like really high scores what we're aiming for, right? That's in like the tens of thousands, right? And so if it's just 100 out of like 10,000 versus 99 out of 10,000, that difference is like extremely small. So to counter that, we what we can do with our fitness value, with our fitness function, is you could like have it exponential. So the higher the score, the like the more uh, the fitness value increases exponentially. So that way, now instead of like having a very small difference, that number being one increased is like the difference from like 2 to the 99 versus 2 to the 100. And so that'll increase your fitness value and let you mutate with the better dinos more often. And then lastly, neural networks. So you guys have probably heard of this. Once again, it's kind of science related. It's based off a real brain with like neurons and stuff. I don't really know how our brains work because I'm not too good with science, but basically, you have a lot of layers. We have a simple diagram on the right. The first layer is almost always going to be your input layer. So those are the sensors from the environment. So for example, let's say at this frame, the sensors might be the dino is 5 feet away from the cactus 2 feet tall, the speed is going like 10 miles per hour. I don't know, just for example, right? And those might be like your sensors. And then your sensors might also be like, there is no bird in the sky, blah, 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 whatever. And then next you have hidden layers. It can be multiple. Normally it is multiple. And so those don't like have like a specific label for what each like neuron or node is representing. Um, but I'll talk about it a bit later, a bit more in depth. And then lastly, you have your output layer after your hidden layers. So the output layers, those are your actions, and those are run, jump, and duck, right? And so basically how it works is you get your input layer, you get the sensors from your environment, it does some magic inside your hidden layers, and then it comes up with your output in your output layer. And you can think that each of these circles, neurons, nodes, like have a number, right? And the higher between 0 and 1, so it's like a weight. And then the higher the number, like the more of it is getting represented. So if it's very obvious there's a cactus in front, then you want your input layer to show 1 for cactus and like 0 for bird, right? It's obvious there's a cactus, not a bird. And it keeps on going. And then it also has zeros and ones in the hidden layer. And then the output layer gives you some sort of percentages between 0 and 1 for each of your 3 actions. And then whichever percentage or whichever number is the highest out of run, jump, and duck on your output layer, is the action the AI is going to choose. And you see there are a bunch of connections here, right? With a bunch of lines and stuff. And those are like the connections from node to node, from layer to layer. And they also have lots of weights and biases. And you can also have positive and negative connections, and we'll show that in a second. And so there's also lots of linear algebra when doing this. The way like most simple machine learning algorithms work is all this hidden layer stuff. It's just matrices multiplied by other matrices. So hopefully you guys know what a matrix is, but it's a lot of matrix multiplication and lots of linear algebra. So actually I had something from here that I'm gonna kind of use real quick. I found this like post on Reddit like a while ago. But basically, it has an example of neural networks and it's pretty good. But basically, what it says is that the little league team, right, baseball team, whatever, you coach just won a big game, and you ask them if they want to go out for pizza or for burgers, and then each kid starts screaming their preference, and you go with whatever was the loudest. So this sentence here that kind of represents your input layer, right? You get all of the sensors, and then they're all different levels of like loudness or screaming from 0 to 1. And that's basically how the neural net works on multiple levels. The top level nodes get some input, they detect a certain property and scream when it sees it. The more intense, the louder they scream. So now you have a bunch of nodes screaming, blah, blah, blah. I'm just gonna skip over it. But this is the most important part is that no one tells them when to scream and it's based on the feedback. So for example, if the team went for burgers and some of them got sick, next week they might not scream for burgers as loudly. And so they have collectively learned that the burgers might not have been a great choice and are likely to lean away from the option. And that's basically how it works. From each node, from each layer to layer, it just like keeps on screaming and correlates different things to different things. So now coming back to here. So if your input layer screams that it's dark, it's red, it's round, then hopefully your hidden layer can add up that to make some more complex features. For example, like as a face, as fur, and until your output layer gets is a kitty. Um, However, there is like no way to tell what your hidden layer like really represents. And so you just have to hope that your AI can learn that for itself. And that's where it starts learning by itself. And so I think now kind of show how everything works. That was all for the terms. So I have a GitHub repo here. I didn't create this. I just downloaded it, cloned it from GitHub. We'll link the docs later and stuff. It's in JavaScript, mainly because I like JavaScript a bit more than Python. But Python's probably more often used and probably a better choice, especially for machine learning. But you can see it has all of these files, and I'll get to them later. I think first though, I'm going to show the thing in action because that'll be more interesting. Oh, typos. So I'm gonna run a server on 8080. All right, so down.html. So this is what it looks like. And basically, you see a bunch of stats, a bunch of stuff here. So we'll quickly go over them. Alive 300, that's how many dinos we have in our population. We currently have 300 of them. Alive percentage, 100%. None of them have died so far. Your fitness average, so far is just 0. The target score we're looking for is 1,000. Oh, by the way, like almost all of them have just died right there. And the speed of the game is like 4.5 and it slowly increases. And the high score currently is 0 because no one has a high score yet. This dino score is right here. This is the first generation and it's currently evolving. This slider goes from 1 to 100 and controls how fast the game goes. So like we can simulate it to be like really slow, which is kind of boring. So we just go to 1, which is the fastest, and just show how it works. Um, the reason why this dino is so smart is because I think I might have trained it a bit earlier. So I guess I shouldn't have done that. But yeah, that was kind of a problem. But it's okay. Anyways, this is an important part though. After generation 2, it shows the neural network of the brain of the last champion, right? So basically that last guy that we just saw who like survived the longest, that was his neural network or the dino's neural network. And you can see all of their input layers: distance, next obstacle, height, width, bird height, speed, and bias. And then you can see this is a hidden layer. It actually has 2 hidden layers, but it's just represented like this. And then these are the run, jump, and duck, the output layer, which are the actions, right? And so the blue lines represent a positive connection, positive correlation. So for example, if we take distance to next obstacle to this hidden node right here, whatever this is, It's saying if the distance of next obstacle is like being weighted, if it's showing up, then it correlates with this one kind of strongly. However, if speed is showing up, then it doesn't correlate with this one kind of strongly. And then the level of intensity of the blue and red connections, so like how intense the connections are from node to node. So the more intense, like the more certain you are that this node correlates with that node. And it just keeps on going. All right, so I think I covered everything here. So look at the code real quickly. HTML file decorations.js. This is the decorations, the cloud, the dino, all that stuff is not important. Also, really important, I want to mention is the reason why we're using this game here. We're not using the Chrome Dino game, right? This is the Chrome Dino game. That's fine. We're not using this one because, and we're using our own built-in game. It's because of a number of reasons, but the main reason would be that if we were to use this game right here, right, the Chrome Dino one, there's no way for us to like grab the input from it like automatically unless we're either A, taking screenshots frame by frame, or B, we are using the console, right, and using some JavaScript functions. So how you would do it if you were to take it frame by frame was you would literally snip frame by frame. You would want to package those images into probably a group of 4, and then you would want to lower the resolution, right, to save compression. You want to compress it, lower the resolution, save some megabytes. You want to convert it to purely black and white, so it's easier for the computer to recognize the different pixels, and then you would send it over. And and then you send it over through a convolutional neural network, which we talked about before. And that's kind of time consuming and kind of like unnecessary. So that's why a lot of times, like with just AIs in general, you will see that the game is like hard coded in like from scratch. And another note is this game, it speeds up extremely quickly, or like much more quick. It speeds up faster than the Chrome version, which allows the dynos to get trained a bit better. So on, so allows it to get trained faster, basically. So this dyno.html, we'll get to it more later. This is a genetic external algorithm, right? The genetic algorithm basically creates populations, and then it does some some stuff here, and you see a lot of matrix stuff here because it's using matrix.js. We'll get to it later. And then this is the mutate. So after each generation is over, it mutates so and so, chooses the best ones using the function find best. And their fitness function isn't too special. It's literally just a reward. It just chooses whichever dino has like the highest score from the last generation. And then this is matrix.js. So this is where like all of the magic or like the math happens. It's a lot of high level math. Uh, yeah, most of things are represented via sigmoid. We're not going to get into it though because it's not worth the time. And then multiply matrix. Basically, this is where all of the neural network stuff is going on in matrix form. Obstacle.js. This one's pretty simple. It's for the game. It creates the obstacles, and it calculates like when it's moving, right? Because like the obstacles have to be simulated as if they're moving towards the dino. And then basically the obstacles are just used in the game and not in the actual like AI, so on. So visualize data. This is all just code to show all of this text on the screen. So like the alive, the high score, the generation, the brain, all that stuff. So this part's also not too important when coming with like the AI itself. And then player object.js, this creates the player or like the agent that we're looking at. You can see fitness starts at 0. These are arrays, right, which are going to be matrices for inputs, hiddens, outputs. That's for our neural network. And then this is a draw function. Just going to skip over it. Collide function. If the obstacle ever hits the dino, the game's going to end. And then this is a look function. This is where we collect sensors from our environment. It's pretty simple because the game is hard coded. And then this is a quote unquote think function. The think function is where the neural network happens. It takes the hiddens, the outputs, and it basically chooses which state, which action it wants to take based off your neural network. And it actually has a bot mode. There's a bot hard coded in here. It's very similar to what Lucas mentioned earlier, though I'm not going to show it because it's not the purpose of what we're showing right now. And then lastly, dino.html. So this is where a lot of the stuff, like the variables that you can control that you can actually write and tamper with, are they're right here. So this is just basic stuff, the images to make the game. And in the cloud, our target score is 1,000. We can change that. We can change some other stuff here, but most of this is unimportant. Um, However, what we can change, which is kind of important, is where's population? Pop size. Right now I have it set to 300. It originally was 100. So we can change it to 100 and save it and reload the page. And you can see now we only have 100 dinos. And so it might not seem like much of a difference, but actually it does learn at a bit slower rate because there's less dinos to be learning from. And then we can also up it to something like 500, which gives us a lot of dinos, which should make us learn a bit faster. And it actually comes with a replay functionality too, which I'm going to show. So I'm going to let it run in the background for a while. So hopefully it can like reach a higher generation. Then we can show how it can replay the best champion from each generation. I'm not sure why it's going so slowly. I think it speeds up after the first cactus though. Yeah, I think that's a bug. Okay, anyway, so let's just play in the background. And then this is the neural network setup, right? The number of nodes we're gonna have. The reason why you have 6 input nodes is because as you can see from here, we have 6 sensors. So this is 1, 2, height, 3, width, 4, 5, 6. Those are 6 sensors. And they show up on the game also. And then we have hidden nodes. Well, we have 6, and we have output nodes, right? Because there's 3 decisions: run, jump, and duck. And that's the mutation rate. Pretty self-explanatory how often it mutates, 0.15. We're not going to change it. And there are some regular variables. You can turn this to true if you want the bot to play. And then basically you have a loop. Now it checks if it's replay mode, which I'll show in a second. And if it's not, it just calls all of the regular function, drawing the game, looking, think, right? All of these are players from player object. And it just runs a loop and it just keeps on going generation by generation. There's not too much else important here. So I'm gonna run this for another minute or so. Hopefully, it reaches like a couple of generations so I can show the replay function. All right, I really should have restarted it. All right, well, I'm hoping he didn't like die soon so it can move on to the next generation. I really should have recloned the repo so I would have restarted. All right, well, that's unfortunate. Uh, if if this guy doesn't like die within the next minute, we'll just call it a day. Otherwise, I'll show the quote unquote replay function. All right, so it's 110 now. So I guess I'll just call it a day. My bad. I should have recloned the repo and had it like restart. So like it wasn't so smart already. But basically that was it for today's lesson. Next week we'll go over the USACO contest, which is coming up on Friday. And then that's all. If you guys have questions, you guys can message right now. Otherwise, I'll close the meeting in a couple minutes. All right, I'm gonna end the meeting now.